So the talk is about excess and tangents of sub-Riemannian geodesics. It has to do with the regularity problem of length minimizing curves in this setting. And I will talk about some joint work with Alessandro Pigati, who is now in Zurich, and Davide Vittone, who is a colleague in Padova. And I will also show you some work in progress that is checked in some situations, but not yet in full generality. So, and let's start. So we are in our setting. We have a manifold M, and with a distribution D, with a metric on D. So locally, the distribution is given by a certain number of smooth vector fields, let's say R, that satisfy the Hofmann condition, as we know. What I'm going to show you, well, we check that when the rank of D is constant, but I'm pretty sure that it also holds when the rank is not constant, but we checked for a rank constant. And then we know that there is a distance, the Carnot-Caratteudori distance on M. And then we have a metric space, M, together with this metric D. It is a length space. And the starting point is this proposition. If the manifold M with this metric D is connected and complete, it should be always locally compact. Then you have an existence theorem for length minimizing curves. So given a pair of points, you have a curve, a horizontal curve, which at least one, maybe many, in many cases we have many of them, but you have at least one curve that has minimum length, and it connects these two given points. I should call it a length minimizing curve. I will call it a geodesic, which sometimes refers to the to extremal curves, which is a bit different. And this curve, well, this existence theorem is more or less standard. You have it in length spaces, actually. And you use Ascoliart-Zelat theorem in the setting of Lipschitz curves. And so you find a minimizing Lipschitz continuous curves. And so a priori you have the Lipschitz regularity. So the minimizer has the Lipschitz regularity. That's the starting point. And the question that we all know, well, the basic one is this. Given a geodesic gamma, is it C1? Many of us probably think it should be infinity, if everything is infinity. But the basic question is it at least C1? Clearly after arc length parametrization. And we are not able to answer to this question. I will show you a very small progress on this question, which is very small, but still a positive epsilon. And so troubles arises from this observation, which is collected in this proposition. So we can find a manifold M, a distribution D with a metric G, and actually in this is also a Lie group, a Carnot group, such that and now M actually will be Rn, such that if you give me any Lipschitz function on some interval 0, 1, any Lipschitz function, and then I take this curve gamma, where the first coordinate is your given Lipschitz function, and then all other coordinates are suitably given, well, this curve gamma, first, it satisfies the first order necessary condition for optimality, the ones given by Pontryagin maximum principle. It will be an abnormal curve in that setting. And secondly, it also satisfies the second order necessary conditions for optimality, which are known in optimal control theory as the go condition or the go condition. And
do you mean with a smooth horizontal distribution in a smooth metric?
yes, M will be a Carnot group, G will be a left invariant metric, and D will be the first layer of pure Carnot group, so the canonical setting. The dimension of M will be a little bit big, but you have this example. So starting only from the first and second order necessary conditions for optimality, you are stuck to the Lipschitz regularity that you had from the beginning. So to prove any further you can you could this one is not, but actually if you you're right, I'm not, you can do this parameterized by arc length. Yes, you can do this. You can do this. So you have this curve and you cannot reparameterize it in such a way that it becomes C1 or anything. It will stay Lipschitz, but you're right. It's a bit imprecise here. Now, so we need new ideas to get any regularity. There was some work concerning corner type singularities, and the topic is somehow related to those kind of techniques. But we have a small improvement of that. So now I'm defining what the tangent cone to a horizontal curve at one given point, what it is. So we can assume that the manifold is Rn. We fix a point, and then we choose exponential coordinates of the first kind. So now we are in Rn. We know that the distribution has a stratification, and this stratification gives us weights, and then we know that we have some nice dilations. This mapping delta lambda for any positive lambda. W1 will be 1, then some 1s, then 2, 3, and so on. These are the typical ones that we already saw them yesterday, precisely those ones. And so I'm working with these dilations at the point x0, which now will be 0 over n. Then we know that we have a tangent structure, which is used taking the vector fields and looking at the Taylor development and taking the leading part, more or less. This will give the tangent distribution D infinity. The tangent manifold M infinity will be Rn, and we also have a tangent metric G infinity. So this will be the tangent structure at the point x0 that we have. We have this tangent manifold. And now take any curve gamma horizontal, so gamma dot is in D, and at the point 0 it is 0. We are fixing that point. And now we have a very natural definition. The tangent cone of the curve gamma at this point 0 is the set of all horizontal curves in the tangent structure. Let me call one of them kappa, such that we can find, this is very delicate, we can find there is one sequence of scales, these positive numbers eta I, which are infinitesimal, and if I blow up in the correct way the curve at the point 0, at time t, we have the pointwise limit, and we reach the curve kappa. And this convergence is for any t, and actually you can require that it is locally uniform. Actually, this comes from the compactness. You always have this. This tangent cone is always non-empty. easy compactness argument, but it may contain plenty of curves, a huge amount of curves, anything in principle. So we would like to understand this tangent cone, this tangent cone at one point. So this is the tangent cone. So our first theorem is the following. So take your sub-Riemannian structure MDG. Take a length minimizing curve, fix a point on the support of gamma, which is not maybe an end point. Then the tangent cone contains at least one line. What is a line? The tangent structure M infinity, the manifold, is Rn. So a line will be a horizontal line, the trivial one, passing through 0. That's a line. So this is the theorem. So at any point you take the tangent cone, there is at least one line. There is, and the next slides will try to show you the proof of this claim. And I hope to be able to understand why we must choose a suitable sequence of scales to have this line. But so this is now my goal. I need some work, some preparation works. We have other results which are a preparation to this. I need to do some work before. So this is our goal. Yes, please.
The cone, does it have some homogeneity property?
What do you mean? Yes, the word cone suggests something.
Suppose you have something inside and if you dilate it, stay inside.
Yes, probably this is true. But the limit curves are not homogeneous. I mean, are not delta lambda invariant. Otherwise, they will be a cone itself. So a corner, a line, no. You may have really anything. The curve may behave in any willed way. Now, if we were able to prove that that tangent cone consists precisely in or of one line, this would mean that we were able to prove that the minimizing curve is differentiable at any point, which we are not able to do. Yes, and actually we would get the Pansou differentiability because this is the correct notion. And even if we were able to prove that, so at each point we have only one line, this is not yet the C1 regularity, because then we have the continuity to prove. So that's a comment. Now, as a corollary of Theorem 1, we obtain a result which was proved some times ago by Leonardi and myself, and more recently in the correct generality by Ledone Hakawori, which is theorem number 2, which is the following. So take a length minimizing curve, then gamma cannot have corner-like singularity. And the reason now is very simple, because if you take a corner point, this means that you have a right derivative, a left derivative, and they are linearly independent. So when you do that blow up, in the blow up, you will have a straight corner, so two half lines. It will be unique, so that's not a line.
This is Theorem 2 is an alternative, and you provide somehow an alternative proof to
I cannot answer yes, because some ideas, so the cut technique and adjust technique is more or less the same. Still, now that kind of technique, we have a very now concrete and general algebraic and effective way to do that. So we have some improvements even in the technique. But at a certain step, we need to do something like that. Still, it's a bit more general.
No, it's a corollary.
That's a corollary. So theorem 1 implies 2, but theorem 2 does not imply 1. Now I would like to discuss with you a limit of theorem 1. Consider this spiral, which is a double logarithm spiral. That one. This is a planar curve in the plane. It is defined like that. On the left, you see a picture. This curve is rectifiable, near 0, I mean. So that the length is finite. And when you do the blow-up, when you compute the tangent cone of since it is very slow, if you look at it at some scale, you almost see a line. But this line, the angle, I mean, depends on the scale. And the tangent cone, that's an easy exercise. The tangent cone is the set of all lines through the origin. So you have all these lines. They are all in the tangent cones, and they are lines. So theorem 1 is empty in this case, because in the tangent you have a line, but then you cannot say anything about the original curve. This means that theorem 1 does not cover this kind of singularities, which may appear, in fact. Theorem 1 is empty in this example, and the spiral has finite length, okay, fine. And 3, this curve, this double spiral, may appear as part of the coordinates, of the horizontal coordinates of an extremal curve in some sub-Riemannian setting, in a group, actually, in a Lie group. It could be an extremal. First order necessary conditions fine satisfied, even the go conditions satisfied, and you have that. And so that's a problem. If you want to do some progress on the regularity, you must be able to study this. But this is only one example of what could happen. Now, there is some work in progress, which is a work in progress, but I studied this spiral in some sub-Riemannian settings, not yet in full generality, and it does not seem to be length minimizing. So in the examples that I studied, it's not, and I have the feeling that it cannot be ever in any setting. But you need ad hoc computations, and these ad hoc computations are very much tailored to this specific spiral with a double logarithm. So the situation is difficult. Now I'm beginning to show you the proof, or a sketch of the proof of the main theorem. So our goal is to find a line in the tangent cone, at least one. And we need two lemmas. The first is this one. Assume that gamma bar is in the tangent cone. So it is in the horizontal curve in the tangent structure. Then take a gamma double bar that is in the tangent cone of gamma bar, in the tangent of the tangent, in a way. Then gamma double bar is already in the original tangent. This is easy to prove. This is not difficult, and this is not deep.
This
But
is the
then
tangent still at the same point.
at the same point. Now we need this because 0, we are in Rn, 0 is in the manifold, in the tangent manifold, so that's fixed. I guess you can do something, you may vary some tangent points, but I didn't check that. What we needed is this, and this is not deep. Then another lemma that we need to use, as you will see, is the following fact. If gamma is length minimizing in the original manifold, and you take gamma bar, which is in the tangent cone, this gamma bar will be length minimizing in the tangent. And hopefully now we have a very detailed, this is not easy, there is an amount of work to prove this, and hopefully now we have a very detailed proof of this proposition number 2. So if we go in the blow-up, so in the tangent, we are still in the tangent and we still have minimality. So please remember these two facts. So now, without loss of generality, we can assume, because of these two lemmas, that the manifold is Rn, okay, and actually it is a stratified nilpotent Lie group, a Carnot group, because the tangent, well, now here there is some work to do, because the tangent manifold is only, how to say, homogeneous and nilpotent. It's not yet a group, but then we learn this from Frederick's paper. You can desingularize, you can lift, and you can find a bigger setting where you have a group structure, and then you lift, you preserve minimality, and you can do.
No, you mean isometric. Your nilpotent stratified group is geometric, invariant metric on this guy? Or?
No, what I mean is the following. If the original distribution is equiregular, then actually you have a Carnot group, a nilpotent stratified Lie group, and that's that. And the metric will be the tangent metric, which will be left invariant. Okay. That's what we have. Very concrete. If you don't have equiregularity, then you lift in the correct way and you're fine. And so we know that the Lie group has this Lie as a Lie algebra with this stratification. V1 is the first layer, it is the generating layer, we know this, and now fix left invariant scalar product on V1, which could be the one coming from the blow. Good. Now I'm defining the first notion, which was in the title of the talk, the notion of excess. Actually, we will have two different notions of excess. This is my first one. Now, take a curve gamma, a horizontal curve. It is parameterized by arc length. So gamma dot is 1, as length 1. And look at here now. Well, here, you see, fix a vector, a unit vector in the first layer, a unit vector B. Then form the scalar product, gamma dot with V. V is a constant here. Then take the square, integrate on some interval, minus eta eta, divided by the length of the integral, take the L2 norm of that, and then take the best V. Take the minimum. That infimum is actually a minimum. Take the minimum. We call that the excess of gamma on that interval. That's a definition. And we will work with this definition. I have two very easy comments concerning, three easy comments concerning this definition. The first one, assume that this excess is 0. This means that you have a V such that a unit vector V in the horizontal first layer such that that integral is 0. This means that gamma dot is orthogonal to V at any time t. This means that gamma dot is in a proper subspace of V1 but then assume that gamma 0 is 0. This means that gamma will be in a proper subgroup. And the new subgroup, the new group, well, the rank will be the original one minus 1. We can make the rank decrease. If that's trivial. Good. Now, assume that the rank now is 2, is precisely 2, and if the excess is 0, it means that you have a V, and gamma dot is orthogonal to V. Then gamma dot is constant, maybe up to the sign. But for minimizing curves, the sign will be always plus 1 or minus 1. So if R is 2 and the excess is 0, then gamma is a line. That's a line. Not difficult to believe that statements 1 and 2 still holds in the infinitesimal version, meaning that if the first excess, this one here, is infinitesimal, then I can find a curve in the tangent cone such that it will be in a proper subspace. Assume that this excess is not 0, but it is infinitesimal when eta goes to 0. Then I hope you believe that you believe me if I tell you that then this would mean that in the curve, if the curve gamma is converging to a tangent curve for that sequence of etas, then that tangent curve will be a line. Oh, well, no, it will be contained in a proper subgroup, and if the rank is 2, it will be a line, the curve in the tangent cone, if this excess is infinitesimal. Very good. And so this is statement number 3. It should be clear. Very good. Now let's go on, because now we have this theorem number 3, which is actually the core of the proof. And now take a length minimizing curve, fix a point. This is not written there. Fix a point, an interior point on the support, assume it is 0, define the tangent cone, and so on. Then there is an infinitesimal sequence of scales eta I such that xs is infinitesimal. This is a theorem. I claim this. You can find a sequence of scales eta I such that the excess is infinitesimal. This means that in a curve in the tangent cone, we can iterate this theorem number 3 first using this claim 1 here to reduce the dimension of the first layer to dimension R2 equals 2. Iterate, get that. And then, as soon as we reach the rank dimension of V1, 2, we use statement number 2, and that curve will be a line. And that line will be in the tangent of the tangent of the tangent of the tangent, but then it will be in the original tangent.
Small problem.
Yes.
When you reduce the distribution, maybe it's no more a Carnot group. You lose some brackets.
I don't think so, but wait a minute, because what I was thinking is that, well, if you have that proper subspace, you will take the Lie algebra generated by that subspace, and then the corresponding Lie group. That will be the Lie group you are working with. Yes.
Maybe the
But you will have dilations, and then you can do this.
Okay. It can be much smaller.
Yes, yes,
Okay.
please. But I hadn't thought about this, so yes.
How does this happen for the double spiral?
For the double spiral, it happens then when you do the first blow up, you get a line. Okay, you get a line, and indeed, for the double logarithmic spiral, in the first blow up, you get a line, this line, and then you are stuck, because that line will be length minimizing in the tangent, and you are not able to deduce anything about this.
As a function of eta, what is the excess in the double logarithmic?
I didn't compute this, so I cannot answer. I cannot answer to this question. To this, I don't know. It will depend, probably it will depend on the sequence of etas. If it will depend on the sequence of etas that you choose, different sequences will give you something different according to the tangent to which you are converging. And probably you will have 0, but you will for each sequence of etas you have to choose the right v. That's what's but I didn't check this. So by an iteration argument, theorem 3 now implies theorem 1. I hope this is clear. So now I begin with a sketch of a proof of theorem 3. And now the bad thing is that the proof of theorem 3 is by contradiction. It is by contradiction. So assume that you cannot find any sequence, infinitesimal sequence, such that this excess is going to 0. This means that the excess is larger than a small constant for all small eta. And that's the starting point of the proof. But you see, so we have to argue by contradiction. And if we contradict this, this only means that I have some infinitesimal sequence of etas for which excess is infinitesimal. And this is why we get the existence of one line for some infinitesimal sequence. This is connatural in the proof. This also means, in my opinion, that the proof and the argument is not really clear and conceptually precise. Still, this is what we are able to do. Now, so now we have a curve, and now excess is larger than a fixed constant for all small scales. And now from this condition star, we can draw two consequences of a completely different nature. And the first one is the following. Look at the picture here. We have the black one is the original curve gamma, the black one. Then you see we have these 2 points on gamma, gamma minus eta and gamma eta. No, please. Think of gamma not of the full curve, but only think of gamma as the horizontal coordinates of the full gamma. Think of that. Then you can do this small blue cut there. So I mean that I cut that part of the curve gamma, the curved one, and I replace it by this blue line segment. Then I need to have a horizontal curve. Then I have to lift the horizontal line, the horizontal coordinates of the blue segment to a horizontal line. This is this red part. We grow up a little bit, and then we follow a suitable translation, vertical translations of the original curve, and we finish there in that point, at that point there. We do this, we do a cut. And sure, the red curve will be shorter because the line segment is shorter than the curved piece of gamma. But we have this error, this vertical error, which is the difference at the final points. Now, if you are in this regime of big excess, or not excess far away from 0, then if you compute the difference between the length of the original curve gamma, the length minimizer in the statement of the theorem, and the new one, which is gamma hat, you have a quantitative increase gain. I mean that the length of gamma hat is shorter in a quantitative way, which is given by the length of the interval minus eta eta, and this is why you have this eta, and then you have this excess squared. But the excess squared is epsilon. So you have a gain of length of order epsilon, of order eta epsilon, of order eta, and epsilon squared, that's fixed. Good, we have this. However, as I told you, there is now an error in the final point, so this does not contradict minimality because we have to restore the end point. Otherwise, now there is a second consequence of this star, which is the following. Now, this statement 2 it's a claim. It's not now easy to explain it. I will try to do this, but so if excess is big, larger than eta, so the excess, where was the definition? Here. So here, this quantity is big. This means that you cannot find any v making it small. That's now you walk a little bit, and a consequence is the following one. You can find small sub-intervals of minus eta eta there. You can find r of them. R is the rank, such that if you look at the horizontal coordinates of gamma, these will be vectors in Rn, and form these differences, gamma tilde beta 1 minus gamma tilde a1, this will be a vector in Rn, form the matrix, compute the determinant. It is larger than a constant, depending on eta of the excess, and then there is a normalization factor. This is r, because you have r of them. From an infinitesimal point of view, this means that assume to replace these differences by the tangents, if you have them. This means that you have r points along the curve where the tangent vectors are linearly independent in a quantitative way. That's a point. If a piece of gamma is a straight line, no hope to do that. It must do something bad to have all these tangent, this linearly independent direction. Now, so now this lemma gives us these positions, beta 1, beta 2, beta 3, and so on, these sub-intervals. And there we perturb the curve in the following way. Where is it? Here. Take one of these interval, AI, BI, and then take a VI, which has to be chosen in a very careful way, but this choice is algebraic in the end. I'm not going to explain you this. Choose a VI also in the higher layer, and typically in the higher layer, and we construct a perturbation of the curve we are used to say that we put there a correction device. So we are here. We go from this green point here to the point there, which is the original one plus x of b. And we follow a geodesic, maybe to go from there to there. We do that. And then we follow a translation of the original curve. This one, it will be a translation of that. We have a Lie group we can translate here. And then we go back, and then we follow the original line. There will be an error in the final, also in this case, but now we have an algebraic machinery to keep track of all these errors in a very explicit way. And now the proposition, the end of the proof is the following one. You had the error, do you remember it? Gamma hat 1 minus gamma 1. This was the error after the cut. Then we can put several devices. Actually, even here there is hidden an iterative construction. We first corrected one piece of error, and then another one, and then another one, using an iteration argument. But there are correction devices such that they correct the final error, and now you add length, and the length will be more or less the distance, let's say the length of v, if this has a meaning. And you sum up of all the length, all of the costs of these devices, and this sum is a little of eta. We can do that with a little of eta. And so now we are contradicting minimality. And this is the end of the proof. And so we have a line in the tangent cone for some infinitesimal sequence. How much time do I have? I have
15 minutes.
So I can tell now. I can show you. Yes, please.
What you prove is that you have a tangent which is contained in a line, right? It could go this way, right?
Yes, yes, you are right. But that curve is not length minimizing, and you know that if you have a length minimizers, the curves in the tangent are length minimizers, and so you exclude that. Otherwise, you would have that, right? May I go on? Now, this is a work in progress. We do not have papers about this, but nevertheless, I will show you something. I will show you how now the story could go on. But since I checked my details only in this example, I will speak only about this example. Now, assume that now that the rank is 2, we have 2 vector fields, and moreover, the second one has a very specific, still general structure. You see, x1 is constant, and x2 is this one. You have these coefficients there, which are monomials of the 2 variables x1 and x2. I'm not considering they may appear in general higher degree variables. That makes things a little bit more complicated, but now I have the feeling that we can manage also that case. Anyway, this is my example. So we have these powers. Assume that in some coordinates this will be you have in a Carnot group of rank 2, so you have left translations and so on. Now, I have a second definition of XS, which is actually the more usual one if you know a little bit about geometric measure theory. Let me comment a little bit on this new definition. Now, we fix a direction. which is a horizontal direction, x1. That's fixed. That's fixed. Now, the excess of a horizontal curve gamma at a point 0, I am assuming here that gamma 0 is 0 probably, or probably this 0 will be the time t, which is 0. Now gamma of 0 can be anywhere. And then we have the interval or the scale eta there, and then compute this gamma dot minus x1. We could be here in the Lie algebra, and we measure the length, and then we divide by the length of the interval. I could take a square root, but in this case I didn't. I'm sorry. This is my definition for this. Now, if this excess is 0, this means that gamma dot is x1 at any point, so it will be the integral curve of x1. That's the mean. If at the point at time 0, the tangent of gamma is x1, this quantity when eta goes to 0 will be infinitesimal. That's easy. If at other points we have the tangent line of before, and we take that suitable scale of etas, then our excess will be infinitesimal if we take as x1 the tangent direction. Now, one first lemma, which is not actually very difficult to prove, is the following proposition. In geometric measure theory, this estimate is called the height estimate. So the height estimate tells you that if you have a minimal surface, the surface will be contained in a very thin slab, and the width of the slab is controlled by the excess, where now the excess is defined using the normal to the surface. Now, let me comment a little bit on this estimate. You see here, gamma 0 is 0. You have a length minimizer parameterized by arc length, and then for any time smaller than eta, the ith coordinate, we are in arena actually, so we are the standard coordinates of gamma. Take the ith coordinate of gamma, divide by that power, which is singular, t to the power, take the square root. This will be smaller than the square root of excess times eta. If this square root of excess is small, this means that the curve gamma is contained in a very thin tube, where the width is governed by excess. And actually, this is something more, because you also have this disturbing weight. Still, you are there, even with the weight. Now, this is the height estimate, or I should call it probably a tube estimate. You have a tube estimate. Very good. Now the key point. This is useful. This is a lemma to prove the following corollary, which is a theorem actually. And I gave a name to this corollary, which is geodesics are almost graphs, because we have now a theorem which tells us something, but still. Anyway, there is one point that is very critical when you study sub-Riemannian geodesics. As you know, one typical example is the one of the Martinet distribution. If you take minimizing curves, it may happen that they are maybe a graph along some directions, but then suddenly they must go on, and then they must go back to reach the final point that they have to reach. there is something like this. And this kind of phenomena are related to, I guess, to the rigidity of the curve, are related to the singularity of the sphere at the final point. So you see, at those points, you lose the property of being a graph. But this is only rubbish. What I'm telling you, it's only philosophy to make some propaganda for the next theorem, which is the following one. Now, we are in the original example here. Be careful. I didn't, now we are checking this in Carnot groups. But here we are in our original example. Take a length minimizer parameterized by arc length, which is 0 at 0. Then, for any epsilon, for any positive epsilon, there is a subset of the time intervals, actually not of -1, 1, but it must be inside of -1/4, 1/4 there. And there is a curve gamma bar defined there doing the following. Where is it? First, this new curve gamma bar, which is defined in a very wild set, this I. I will be closed, but a mess. The support of gamma bar is inside the support of gamma. So we are selecting a part of the support of gamma. That's one point. Secondly, if you look at the coordinate of, at the first coordinate of gamma, this gamma 1 of gamma bar, actually, so take gamma bar 1, this is t. So this means that gamma bar is a graph along x1. We have a graph. This gamma bar will be a graph along x1. Good. And this graph, can you see the dot there? This is the group law. This wy, these are the natural weights. I hope that you recognize here some homogeneous norm, a piece of a homogeneous norm. Inside we have the ith coordinate, and I is 2, 3, 4. So, and look at here, you have a Lipschitz constant, that's epsilon. So, for any epsilon, the curve gamma bar will be epsilon Lipschitz. So, almost very flat, very flat. So, it is a graph, epsilon flat. The support is a subset of the original curve. It is a graph. It is epsilon Lipschitz. And third, if we look at the length of the original curve, which is not covered by the new graph, because there will be a missing part, which is not covered inside a ball of radius 1/4 there, then this length is very small compared to excess. So if this excess is small, maybe if this is 0, this means that the length is 0. This means that gamma bar is gamma, actually. So you are covering everything. And you have this very precise quantitative estimate. And now we are here. This is the last theorem that now we could prove. Now we are checking the details of the proofs to give a general statements. And this kind of result here in geometric measure theory is called the Lipschitz graph approximation, which is the very starting point of the regularity theory of minimal currents. If you have a minimal current, the first thing you do is to approximate it by a graph, a Lipschitz graph, using an analogous theorem. So we have the theorem here, the Lipschitz graph approximation. And we have some ideas how to go on from this, but probably it is better to stop because my ideas are not very clear and not yet very effective. But in the regularity theory of minimal surfaces, what now you do is a blow-up, a suitable blow-up, and what you get in this blow-up is a harmonic function. You get a harmonic function. The graphs, the Lipschitz graphs, rescaled, are converging to a harmonic function, and then one uses the regularity of harmonic functions to infer regularity of minimal currents. But we are not able to do this part of the project, of the program. So we are working, and who knows what we are able to do. And now I stop. Yes, thank you very much. I stop? No. Probably I have a last one. I don't stop. I have these last slides. So some of the results you can find in this first paper. This is about the existence of tangent lines. And if you want to understand, to see the details about the initial technical part, now we have written, hopefully in a very detailed way, everything in this paper here. So on tangent cones. So we prove that the tangent of a minimizer is a minimizer in a very detailed way, hopefully. Very good. That's all, and you find the paper there in the PISA website. Thank you again.